Hello everyone, this is our Lab 7 presentation. My name is Minjin Huang. Here are my teammates.
Hi, I'm Fei Huang.
Yeah, I'm 志鹏.
Okay, in this video, we build and train a tiny two-layer MLP for Scratch using NumPy only and show three mini demos: 1D regression, binary classification on rings, and three-class blobs. And our network is uh, input to linear 1 to ReLU to linear 2. And here's our hidden activations, and here's our outputs. In regression mode, we use Z directly, and in classification, we apply softmax to get probabilities. And the training loop is mini batch SGD, shuffle, batch, forward, compute loss, backward, and update. We support two losses: mean squared error for regression and cross entropy for classification. Here's the example one. The example one learns a noisy piecewise linear function. And this one. And the model is 1 to 32 to 1, trained for about 500 epochs with MSE. And here are the results. So we can see the target and the prediction almost match. So the ReLU networks are piecewise linear, so they fit broken lines naturally. And the example two is binary classification on two concentric rings, linearly inseparable. So example two. The model is 2 to 64 to 2, softmax plus cross entropy, about 200 epochs. The training accuracy reaches about 99.9%. So a linear classifier can only draw a straight line, but one ReLU layer can wrap the space and learn a curved radial boundary. So the results. So the metric is the results. And example three uses the Gaussian blobs for multi-class classification. The model is 2 to 64 to 3, trained with cross entropy, and the training accuracy is around 95%. The ReLU partitions the plane into many linear regions, so it is usually enough to separate well-formed clusters. The results. We can see the train accuracy. So as shown in the table, the model's predictions are very close to the true target values across the tested input range. This demonstrates that the two-layer MLP using ReLU activation functions was able to successfully learn and approximate the target piecewise linear function with a high degree of accuracy. The key takeaway from this part is to gain a deep mechanical understanding of how a CNN works by implementing its core components ourselves, loading and preprocessing images, performing a convolution, applying max pooling, and training a full connected layer. This hands-on approach reveals what's happening under the hood of modern deep learning frameworks. Now let's move to part 2, application.
Oh, okay, I'm going to share my screen. So part two, in this part, we will work through a simple yet complete convolution neural network. So it implemented in pure NumPy and designed for cat versus dog image classification. And for this part, we want to demonstrate at a low level like how convolution, pooling, and fully connected layers can be built manually and without using deep learning frameworks such as PyTorch. So as you can see in the first cell, we only use the NumPy. So the NumPy will provide the fast matrix and the tensor operations, which will form the backbone of our neural computations. And the next library is to handle the image loading and resizing. And also the matplot could be used for the virtualization. And the first step we will load our data. So in our data site, we have prepared like a one hundredth 10,000 images for dog and cats. So for the cat we have 10,000, and for the dogs we also had 10,000 images. And then we loading our data. So the functions load the data file from the two folders we call it cat and dog. So each image is opened and converted to RGB. We ensuring the consistent color channels. And then we resize to 16:4 multiple for 16:4 pixel for uniform for the uniform input dimensions. And then we normalize by dividing pixel value by 255 and scaling them into the range from 0 to 1 for stables numerical computations. And then each images get a labels 0 for cat and 1 for dogs. And then we split the data file into training and a testing set. So 80% of the data is used for training and the rest for testing. These separations allowed us to evaluate generalizations performance later. And then we reach the helper functions like the ReLU, so the reactified linear unit. So as the activation functions, so it induces nonlinears and can help us to prevent the gradients vanish by zeroing out negative values. And then it is derivative functions can be used during the back propagation for computing gradients. And also we should to measure the mean square errors, which is MSE. So it is the loss functions. So where the MSE is more common in regression, but if here is for simple listed in binary classification, where outputs are continuous and later through and the later threshold is to 0 or 1. And then we have to initialize our parameters, like the convert filters is 3 multiple 3 multiple 3 kernel for convolutions. So it is the small random initialization helps the model learn from scratch. And there, I want to mention that there's a bug in our original code. So the correct the number is 31 multiple 31 instead of the 32 multiple 32. And also, since we use one pipeline here, so we can skip to multiple 3. And the WFC is the weight matrix for the fully connected layers. So after convolution and pooling, the future map size become roughly 31 multiple 31. So we flattened it into that length. And the BFC is the bias term for the fully connected neurons. And then we reach the main function, like we convert 2D, and these functions perform the 2D convolutions operation manually. So it slide 3 multiple 3 kernel over the image and it multiplies overlapping regions and sum them to produce one output pixel per position. And the max pooling, the max pool. So it's reduced the spatial dimension by taking the maximum value in each two multiple two regions. And this not only reduces the computation, but also provides translation invariance, meaning small shift in the input images don't affect the output match. And the forward pass, so will perform the entire inference pipeline. So it will convolution to actual low-level features and RERU activation for nonlinearity and max pooling for dimensionality reduction and flattening to prepare input for the fully connected layer. And this layer computations will all the extracted features contribute to the final score. So the output FC out is a single scale indicating how likely the image is a dog or a cat. So then we arrive at the tuning part. So we have the IRR equals 0.001 and the apex is equals 10. So maybe we use a small learning rate and train for 10 apex. So for each training images, we performed a forward pass and computer lost. Then we compute the gradient for the fully connected layer and then update the parameters to the FC and BC. So this is the stochastic gradient descent. We will update the weight of each sample to minimize the loss. And finally, we will print the process after each epoch. And also, so as we know, we divide our training data set into two parts. So one is for training and the left 20% is for testing. So in here, we will run the model on the unseen data and convert continuous output into a binary class prediction using 0.5 threshold. This resulting accuracy means the model ability to generalize beyond the training site. And we can see when we give the output, so the test accuracy is reached the 100%, but this is a very real numbers. And also, and in the end, we also want to we have code our own evaluation code to evaluate the test folders, which is the mixed data site. So we labeled the cat and the dog in the prefix. So then the code can, according to the prefix, to determine if the output is if we reach the correct output or not. So then also, thing here, the load test data is the load all the test images by reading the file name starting with the cat or dog, and where we automatically and assign labels based on the prefix. So it also skipped corrupted or labels via gracefully. And then the main is called the evaluate test by prefix. So these functions measures accuracy, latency, and throughput. So the key metrics in machine learning systems will help us to get how many prediction are correct and how long each inference takes and how many images are processed per second. And by processing the dataset in blocks, the evaluations avoid memory overflow for large data sets and provide intermediate timing statistics for better for better results. So at the end, we also print out the summary. So the total sample is near to 5,000, but the occurrence only reach like about like 30 of 15%. The time is only used like about less than 2 minutes. So it's very quick. The accuracy uh in the be strong. So in summary, so we manually implement tiny convolutional neural network entirely in NumPy. So each component's convolution, activation, polling, and fully connecting layers was coded from first principles. So the projects demonstrate the mechanisms of deep learnings without relying pre-built frameworks. And finally, we evaluate the model both in terms of classification accuracy and runtime efficiency. And then we are arrive at the part 3.
Okay, thanks Menjin and Zhipeng for sharing part 1 and part 2. I'm going to move to part 3. Let me share my screen first. So, okay, so for this part, so as we saw, in part 2, our simple CNN built from scratch with NumPy give us a baseline. It achieved about 50% accuracy, which is barely better than a random guess. And it was slow, taking about 30 seconds to train on small data set. So in part 3, we're going to solve this problem, these two major limitations, low accuracy and low performances. To do this, we moved from our manual implement to PyTorch, a modern deep learning framework. Mm, So, so now I'm going to switch over PyCharm to quickly walk through the code for part 3. Here is a Python script we used for part 3. So it uses a PyTorch library to build, train, and evaluate our CNN. At the top, right here, we use the same setting as part 2 for a file comparison. And the second part here, here is a important line for this part of the lab because this single line of code is how we this single line of the code is how we use the GPU or CPU. PyTorch checks if a compatible GPU is available. If it is, device is set to CUDA, otherwise it defaults to CPU. So next, from section 2 through section 3, through section 4, this whole 3 part, we just set up our data pipeline. We define the transformation to resize all images to 64 square and convert them into tensor. And then we used subsize. We use a subsize to ensure we are only training on 116 images, just like in part 2. Finally, we split this data into training and testing set. Training and testing set and load them using PyTorch data loader, which handles branching and data for us automatically. So in part 5, in section 5 is this section 5 is the heart of our model, the cat and dog CNN class. This is where we see the biggest difference from part 2. Instead of using a one single fixed filter, we define the proper network architecture. So we start with two convolutional layer, conv1 and conv2. These are the feature extractors. The first layer learns the simple features like edges, and the second layer combines them to learn more complex features like texture or shapes. After the convolution, we use a max polling layer to downsample the future maps, which makes the model more efficient and help it focus on the most important information. Finally, after flattening the output from the convolution layers, we have two fully connected linear layer, FC1 and FC2. This acts as a classifier, taking the extracted feature and make the final decision cat or dog. Unlike the NumPy model where the filter was random, every simple parameter in this entire network is trainable. So we move on to the section 6. We initialized our model and move it to our selected device, either CPU or GPU, using two devices. We also define our loss function right here, and which is a standard for binary classification, and the random optimizer, which is responsible for updating our model's weight during training. So in section 7, section 7 is a training loop. For each epochs, we iterate through our training data. Crucially, inside the loop, we move the images and label to the same device as the model. The rest is standard training process. Get model's outputs, calculate the loss performance backpropagation with loss backward, and update the weight with optimizer. So finally, in section 8 is the evaluation loop. We set the loop to evaluate model and use torch no grad to be more efficient. We passed our test images through the model, get the predictions, and compare them to the truth labels to calculate the final accuracy, which we then print in the end. So that's all our code explanation for part 3. I will go back to say what we should do for this part. So first, our first step was to run the improved PyTorch model on standard CPU. This allows us to isolate the benefits of the framework itself before it even adding GPU acceleration. As you can see right here, we just use this simple file to check our device. We run it, and it will show the result that was CPU. So, and then we run this code on the CPU device, we can saw the result. Just a moment. So as you can see, the result was already better. We achieved the test accuracy about 16%. 60%, a huge. It's not the huge, but a big leap from 15% we got with NumPy. And the training time dropped from about 30 seconds to just 5 seconds, about 5 seconds. This shows that simply using an optimized framework like PyTorch, which has a highly efficient backend and allows us to build a proper multi-layer trainable network, provides a massive improvement in both accuracy and speed. So for the second part, we're going to run exactly the same code on the machine with GPU. So also we can check the device first. As you can see, our GPU now the CUDA is available, and our GPU devices is also available. So let's just the only change we do for this part was telling PyTorch to use the GPU for its calculation rather than CPU. So we can also run code, the exactly same code. As you can see, it's much faster than CPU. So the result here improved even further. Our final test accuracy is about 70%, and the training time was cut down again from 5 seconds on CPU to just 3.771 seconds on GPU. This incredible speed up is because GPUs are designed for parallel computing. A task like training a neural network, which involves thousands of identical calculation can be run simultaneously on GPU mining cores. This is what makes modern deep learning feasible. So in the last part of this part, we do the comparison from part 1, part 2, and part 3. This table really tells the whole story. Moving from our manual 9Pi implementation to PyTorch on GPU give us a 15% the accuracy boost and made the training 7 times faster. Then adding the GPU give us another 5% accuracy boost made it over 10 times faster than our original model, which we do on part 2. The key takeaway from this lab is clear. For any serious machine learning task, using model optimized framework like PyTorch and leveraging specialized hardware like GPU is not just a nice to have. It is essential. It is an essential requirement. It's the differences between a model that barely works and takes a long time, and an effective model that can be trained efficiently. Okay, that's all for our Lab7 presentation. Thank you.
Thank you.
Thank you.
Bye.